discussed it is because potentially I might have a question on my lab quiz about the ammonium test or on my lab final exam. That's the only reason I discussed that. But we're not going to actually do it. Okay? So the last thing I have to talk about, and this is just for purposes of, in other words, you can, we're talking about note 5 here on page 235. These are the precipitation tests. And I said, first of all, I'm not going to go back over the other ones. You can do the flame test, then you're adding HCl, and then over here we get to note 5, and it says, actually before we got, there we go. In note 3, I'm in the wrong note, page 235, note 3. After you've added the HCl and done the flame test in procedure 27, you may go on and do this part, or if you decide you're going to guess, you can guess. You're going to evaporate to dryness. Add 3 or 4 drops of water. I said that was critical. You scrape around in your casserole and things, trying to get all that material into suspension. Actually, sodium potassium compounds will all dissolve. So will the ammonium compound, but up till now I've been saying don't bake. As I said, for this particular procedure, you're baking a lot because you want to get rid of ammonium because it interferes with the potassium test. And we went through the sodium, zinc, uranyl acetate. I talked about the net ionic equation. We will have enough, in other words, we'll have medium or greater amounts, so you should be able to see it precipitate. You want to dispose of that reagent carefully. You don't want to lick your fingers while you're handling the bottle, anything like that. Then what you're going to do is take the rest of the dry solution. Remember I had the little arrow here? This was the magnesium test. And then over here I went like this. And you did the business where you evaporated to dryness, 4 drops or less. Transfer to test tube centrifuge. Then you took 1 drop of that solution. That was the preceding part. That was your sodium test. This, it says the remainder, but you don't want to suck up any residue that's at the bottom of your test tube. So you're probably going to have 2 to 3 drops, more likely 2. So you're going to take about 2 drops. It says 1 drop of acetic acid. Mix thoroughly. Since it's all liquid, I don't see why it wouldn't mix thoroughly, but it says mix thoroughly. And the next thing it says, add an equal amount. Wherever it says that. Add a volume of the sodium hexanitride cobaltate 3 equal to the volume, which means it's not going to be more than what? 3 drops. So you should have about 6 drops of solution in your test tube. People keep always over the years bring me test tubes with that much liquid in it, so I didn't see a precipitate. And when you get too much liquid, you won't see a precipitate. So equal volume of, and I'm just going to write 3 drops. It's 2 plus 1 is 3. Sorry, pass the test. It's sodium. Now this is a deep amber color, but it tends to break down. And when it turns pink, it won't work right. So if you're going to use the reagent and it looks pink, bring it up to me and I will repair it. So if it looks pink when you go to use it, and I usually look at it before I put the bottle out anyhow to make sure it looks the right color. It's because the NO2 here is eventually oxidized to nitrate, so all I do is add back some NO2 to convert it back to that particular compound. Okay. And you let it stand for 5 minutes. Usually the precipitate forms fairly quickly because the potassium in your solution the sodium came from this side. It's going to make this yellow precipitate. That's indicative of potassium, and it's dipotassium because you could have different ratios. So you're treating it as two cations. This part's easy. Sodium, and then hexa nitrido, and the book doesn't say N, but since we wrote it like this, we're going to say hexanitrido-N. I ran out of space there. Now the only thing that goes wrong here, and I see when people do this test, I used to always, I'm not going to require that you do it unless you want to show it to me. Or you compare your precipitate, because what happens is ammonium forms exactly the same precipitate as potassium. It's the same color, you can't distinguish it, and lots of times people show me when I was checking for the knowns, I'm not going to bother doing that because we're running into experimental difficulties with equipment and things. So I'm not making you go through the known, but if you want to do it simultaneously. But what happens when people get a lot of this, it's because they didn't bake off all the ammonium. Remember, you're adding ammonium oxalate, you're adding ammonium sulfate, you're adding a lot of ammonium compounds as you go along, prior to separating out this last step here, procedure 27. Okay? So if you don't bake right here, it says really bake it until you don't see any more fumes. If you don't bake off all the ammonium, it does exactly the same thing as potassium and interferes with the test. Questions about that? No questions? Okay. Continue here then. Going back to, everybody's up to date on the notes. Erase that. As I said, I'm just going through note 5 here. And for this particular procedure, that's why I said, if you don't want to write anything in your book, you can remember everything. There's not that much to remember. Only 6 ions, really easy equations. Okay. Somebody mentioned mirror images over there. And we're talking about these optical isomers. Now, one of the things I pointed out, the reason they're called optical isomers is because they rotate the plane of polarized light. And one of the things that's part of the nomenclature, which we're not going to do, is use little pluses and minuses as part of the name. You didn't do that in any of these. Next slide does. But we have no way of determining that. There's the RS system nomenclature, which we're not going to bother with in this class. I don't know if Dr. Jones even bothers with that. There we go. Here are some different molecules. All this little minus means it rotates the plane of polarized light counterclockwise or clockwise. And we have no way of knowing it, so it's part of the name. We just toss that in there. Okay? Then he has up here several different optical isomers. And he put the key thing we're looking for, in modern terminology we call it a center of chirality. In the old system, or the way I learned it, we just look for an asymmetric carbon. Asymmetric means it has 1, 2, 3, 4 different groups attached to the carbon. That's what we have here. It doesn't matter whether you pick them iodo or bromo or whatever, as long as there's 4 different groups, it creates a center of chirality, or like I like to call it, asymmetric carbon. And that means it can rotate the plane of polarized light. That's why we call them optical isomers. These are 2 different sugars. Anytime you have a CHOH, in other words, CnH2ON, it's a type of sugar molecule. The OSE indicates that. We're not going to get into naming sugars either. But notice it has different optical properties. And the D and L refer to another way of naming them. Again, we're not going to bother with that. But the interesting thing about it, I mentioned one of the properties is that it rotates the plane of polarized light. That's why we call them optical isomers. But there's one other property. These are sugars. And if you grow bacteria on one of them, the bacteria grow and thrive. You use the other sugar, which is the exact same chemical formula, the bacteria colony dies out. So it can digest one, but not the other. And I don't know if it's this particular sugar. What the explanation is. He drew the mirror image. I want to look at the optical isomer here. In other words, these are just mirror images of the same thing, center of chirality. But I want to compare this molecule with this one, which has the exact same formula. But if your enzyme is set up to do this, and break the bond and digest it, the same enzyme doesn't react with this because it can't get in, or vice versa. So that's one of the explanations. That's another property. As I said, one of the key things is one of the optical isomers, not for these molecules, but one of the optical isomers would be very effective at treating a disease, the other would not. Okay? So this business of dealing with optical isomerism is very important in modern organic chemistry. But again, we're just not going into organic chemistry that deep. So this is another example, and I was preparing this sort of structure because obviously the enzyme is coming this way or this way. So the fact that they're different mirror images of each other isn't that important. But this is another optical isomer. These are not mirror images, and not one of these would be effective or whatever. But notice here again, he drew the mirror image. When you show me about optical isomers, I want to see basically the same structure repeated. And then I'm going to put a little asterisk to show me where you think the asymmetric carbon is. If you can't find an asymmetric carbon, then it will not have an optical isomer. But one of the questions I frequently ask is, draw different structures to illustrate the different types of isomerism that we went over. And that's all you can do with optical ones, because we're not going to worry about naming them. But, this you can name. Because that's just based on methane, or if I want to make it fancier, again, 4 different groups. It's got an optically active thing, so you do this sort of thing. There's my little asterisk. I really don't see. So that's how you would do it, and both of them would have the same name because we can't decide which one's plus or minus, and we can't decide about E and L because we get into that, or E and Z, do, so, or RNS site. Coming back to this thing, whoops, I forgot this sort of thing. But both of these, so far as we're concerned, have the name one chloral. Thing. Because both the bromo and chloro are on there. If we have this thing, notice we have 1, 2, 3, 4 carb hydrogens, 3 and 4 hydrogens, chlorobromo. Does this have an optical isomer? No, because there are two same groups. It's not an asymmetric carbon anywhere. This is called achiral. That's just the modern term that they use instead of saying asymmetric.